Hello class, this is Mr. Lehman. I want to continue talking about waves, properties of waves, and get into more of the calculations involving frequency and wavelength and energy. And so there's two formulas that we're going to be using a lot this unit. The first formula is on the left here, and so what we've found mathematically that the speed of light represented by letter C through a vacuum is 300 million meters per second, or 3 times 10 to the 8th meters per second. And this is equal to the wavelength represented by Greek letter lambda times the frequency represented by Greek letter nu. So wavelength times frequency is equal to the speed of light. So as one of these variables goes up, the other one is inversely related, the other one will go down. So if we double the wavelength, the frequency has to be cut in half. So remember, wavelength is the distance between the top of two waves, and the frequency is how many waves will pass by a fixed point per second measured in hertz. Our second formula is equal to the energy. How do we calculate the energy of a wave? The energy in joules, represented by capital J, is equal to Planck's constant. So Max Planck figured out the relationship between these two variables. So if we take the frequency, Greek letter nu, times Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds, this number h, the constant times frequency, will be equal to the energy of the wave in joules. So let's practice using these two equations. So problem number one, a couple things before we get into the problem. So remember, our wavelengths, we have to have our wavelength in meters, the base unit. We have to have frequencies in hertz, and then we have to, if we have these things in meters and hertz, then we can figure out the energy in joules. So if it's not in the base unit, we have to do some conversions before we plug these into those two equations. And so our first question deals with radio stations. So FM radio stations are in megahertz, AM radio stations are in kilohertz. So if you're listening to the AM radio, 1210, that signal, that wave is traveling at a frequency of 1210 kilohertz. And so from this we can figure out the wavelength, the distance between the two radio waves, the crest, and also the energy that that radio wave is carrying. So if we want to calculate first the wavelength, remember the speed of light is equal to the wavelength times the frequency. So if we rearrange this equation to get wavelength by itself, we have to divide both sides by the frequency. So frequency divided by frequency is 1. 1 times the number is that number. So that cancels out frequency, and so we're left with the speed of light divided by the frequency is equal to the wavelength. The problem is our frequency is in kilohertz. Remember, kilo is equal to 1,000. So 1210 kilohertz. We set it up, dimensional analysis. We have that kilohertz on the bottom. 1 kilohertz, one of our bigger unit, is equal to 1,000 of our smaller units, since we have the prefix kilo. And so we get 1210 times 1,000, which is 3 zeros added onto the end. So 1,210,000 hertz. And so what we can do now is we can plug this number for hertz into our equation, divided by the speed, or the speed of light divided by that number will give us what we're solving for, which is lambda. So we're going to take 3 times 10 to the 8th meters per second. When I do that in my calculator, I like to put that in parentheses. I'm going to divide that by this many hertz. And when I do that, I can solve for my wavelength. If I want to figure out the energy of the wave, energy is equal to Planck's constant times the frequency. So energy is equal to 6.626 times 10 to the negative 34th joule seconds. I'm going to multiply that by frequency. The frequency is 1,210,000 hertz. Hertz are waves per second, so if we have seconds on top, seconds on the bottom, seconds cancel out, leaving us with our answer in joules. So the energy, Planck's constant times the frequency in hertz, will give us the energy. if we look at light, light has the wavelength in nanometers. So if red light has a wavelength of 868 nanometers, how much energy would it be carrying? Remember that combination formula we can use? So energy is equal to Planck's constant times frequency, but remember frequency is equal to the speed of light over the wavelength. And so we can use this equation instead. So the energy of a wave is equal to Planck's constant 6.626 times 10 to the negative 34th joule seconds times the speed of light, which is 3.00 times 10 to the 8th meters per second, all over the wavelength, which is 686 nanometers. So 686 nanometers are 686 billionths of a meter. And so billionths, the exponent for billionths is times 10 to the negative 9th. So even though this isn't proper scientific notation, for the sake of putting it into our equation, we can go ahead and leave it like this. Otherwise, you could rearrange it and make it 6.86 times 10 to the negative 7th. But we don't have to do that. So we can solve for energy if we take Planck's constant times the speed of light divided by the wavelength in meters. Alright, so I hope you help. If you have any questions, let me know. Feel free to stop in for extra help and come in for 8th period. Thank you.